Good morning, student. In continuation of my lecture series on electrochemistry, today I would like to teach the last part of Butler-Volmer equation. As you know that in my last two lectures, I had discussed the fundamental of Butler-Volmer equation. I have dealt with the relationship between exchange current density as well as the over potential. In the second part, I discussed the derivation of Butler-Volmer equation. And if you see your M.Sc second semester chemistry course content, the applications of Butler-Volmer equation is also there. And in sometimes I found that there is some confusion between the Butler-Volmer equation and Tafel plot. So in this elementary lecture, what I am planning to discuss only some of the important application of Butler-Volmer equation. And particularly, I will concentrate on the Butler-Volmer plot, or sometimes it is called the polarization curves. And I will very simply discuss the origin of Tafel plot. And although I have prepared a separate lecture on the Tafel equation and the Tafel plot, that is separate. But here I will discuss some of the application of the Butler-Volmer equation and what is the basic difference between the Butler-Volmer plot and the Tafel plot. What is the role of overpotential? If the values of overpotential is very low, what happened? And if the overpotential values are very high, what happens? So how do we connect this exchange current density or current density and the overpotential? That is my objective. It is a very small lecture. So as we all know that it is one of the most fundamental equation, and of course for studying any electrode kinetics or any electrochemical reactions, we have to apply this Butler-Volmer equations. And this is the simplified forms of this Butler-Volmer equation, and we all know that here is the exchange current density, you all know, current density, that this is actually over potential, and this is current density, and this alpha, you know that sometimes it is called the symmetry constant or the transfer coefficient. Okay. So this is a very crucial equation, and there are two parts. You see, one is related to the anodic current, another is related to the cathodic current. But this equation is very crucial, and depending upon these values of overpotential, we can modify that equation. And with the help of this equation, the electrode kinetics can be understood. That is very important, and it will provide an insight into the rate at which electrochemical reactions occurs at electrodes. Now, there are many applications, particularly when you study the corrosion, when you study the fuel cell, when you study the electrochemical sensors, battery technologies. It has got tremendous applications. So I will not discuss the details of these applications. I will just mention sometimes in an examination point, some short question may be asked, what are the importance of the Butler-Volmer equations, what are the important applications. So of course, I can divide into three parts. First is that battery technologies, in the areas of batteries technologies, whenever we use any lithium ion batteries, or now people are using on the sodium ion batteries. So batteries performance, prediction and energy storage is also very important. And Butler-Volmer equation plays a very significant role to understand the performance, to predict the degradation as well as the efficiencies of the batteries. And it can optimize the electrode material. And on the basis of the results obtained by the Butler-Volmer equation, one can design the battery design. And this theory is widely applied in various types of batteries, including the lithium ion, sodium ion, zinc air, lead acid batteries. I will not, as I have already discussed, that I will not discuss these things. My intention is to just discuss about the Butler-Volmer plots or the polarization curves. And also with the help of this Butler-Volmer equation, it also helps to estimate the internal parameters like reaction resistance, over potential, which are essential for state of health and state of charge algorithms. So when you will study the details of batteries technologies, then we will discuss the details application of these things. Another very important application, you all know that there are a large number of research work is going on that fuel cells, and particularly the kinetics of hydrogen oxidation reactions, or you can call it the evolution of the hydrogen. And second is the oxygen reduction reactions. So this Butler-Volmer equation plays a crucial role in optimizing electrocatalyst design and enhancing the overall fuel efficiency. And the electrochemical behavior of proton exchange membrane fuel cell, of course, is very important, PMFCS, or solid oxide fuel cells. And definitely the Butler-Volmer equation quantifies the activation over potential, because in first lecture and second lecture I have very categorically discussed the role of overpotential, the types of the overpotential and the relationship between the overpotential. When you plot a graph between the current density and overpotential with the shapes of the curves, we can throw light on the electrode kinetics. And third application, very shortly I would like to discuss, one is that sensors. And really it has got tremendous application in, of course, in medical diagnosis or biological sensors, biological electrochemical sensors, like glucose sensors. And second is for the environmental monitoring, like if you want to detect the heavy metals or some toxic pollutants and gas, and of course other industrial process, that equation can be used. And of course it helps to interpret the sensor responses to redox active species. It also models the relationship between the electrode current density and the overpotential, and which is the key factor of such type of things. And corrosion is very, very important. As you know, there are different types of corrosions, and there is a separate, I think, concept of the corrosion. But the rate of metal corrosions by modeling the anodic and cathodic process. I am just, as I just a few minutes ago I discussed about the hydrogen evolution reactions. You know that is a reduction process for the hydrogen generations. And second is the oxygen reduction or the hydrogen evolution process is also there. So one is, these two reactions are very important. One is if we are talking about the metal oxidation, so naturally it is anodic type of the reactions, and if we are talking about the cathodic process, so it is the reduction process. Now I am coming to this today's main aspects, and please listen it very carefully, because this is the starting point of Tafel plot and in final conclusion of the Butler-Volmer equation. So it is very, very important. And ultimately, if we are talking about the polarization curve, so it is nothing but the relationship between the, if I am talking about J is our current density and over potential, whatever the role. And of course, with the help of this Butler-Volmer plots or polarization curve, one can visualize the reaction kinetics at the electrode surface. With the help of this type of plots, we can predict these things with the values of, suppose it is 1, 2, 3 times, so -1, -2, -3. So we can predict the nature of these things. That is the important point. So now with the help of the shape, we can directly plot between this current density and over potential. So sometimes there are symmetric type of plot is also there. And there is an exponential curve which shows both anodic as well as the anodic. I will explain in my next part, and the cathodic branches. And what are the application of these polarization curves? With the help of this polarization curve, general electrode kinetics can be studied. Symmetrical redox reaction can also be studied. Corrosion studies are, of course, you have to study. So what I can say that full kinetic behavior over a range of potential can be studied. Now I am coming to the different types of the curve. Actually, what happened? There are three important parameters. One is, of course, exchange current density. One is eta, and another is, as you know, that alpha. So in the next part, we will see when we plot a graph between the charge density and over potential, what would be the effect of alpha, charge transfer coefficient? What should be effect of exchange current density? I will take different values of exchange current density. I will take the different values of alpha, maybe very low value. Alpha range is 0 to 1. I can take 0.5, I can take 0.1, I can take 0.9 like that. So what would be the effect of this thing? Similarly, I will use different types of electric charge density and other things. So there are some thumb rule. Symmetric means when the alpha A charge transfer coefficient anode is equal to charge transfer coefficient of the cathode, and this is a standard value 0.5. Most of the cases we do the fix this value. So it will produce a balanced curve where in a particular point I will show the graph that the value of like that eta is equal to 0 and the value of current density may be 0. Then of course we will see both the sides like that. And asymmetric plot occurs when this charge transfer coefficient, or sometimes it is called the symmetry constants, are not showing skewed behavior in favor of one reaction directions. Now what is very important, please, so therefore I am giving the yellow color, this special color, that at now what we will do now, we will impose two conditions. First condition, when the over potential is very, very low, and second condition, when over potential values are very high. What happened? Bear in mind that because when you study the details of Tafel plot, just imagine that when the over potential values is very high, the simplified forms of the Butler-Volmer equation is the Tafel plot, the log plot. And when the overpotential value is very low, generally Ohm's law is obvious. So I will explain these things. So generally what I am talking here, that linear region analysis were at very low potential. But we have to prove it, what happens in the low overpotential. Generally, symmetric plots are idealized and used in basic electrochemical analysis. It is a general conclusion. And in the last part of the lecture, I will show you some of the values of alpha as well as that exchange current density at 25 degrees centigrade for hydrogen evaluation using different types of electrodes. You will see the values, and experimental data are very limited. I do not know the reason, because some of the electrochemical parameters can also be obtained by these plots. Similarly, with the help of Tafel plot also we can extract some of the electrochemical parameters. So basically, the asymmetric plots are more realistic for actual electrode process, basically for application part, metal corrosion or the electrocatalysis. But naturally it is for simple system, symmetric plots. And understanding the asymmetric plots, we can model the kinetics, we can design the electrodes, and ultimately if we understand the modeling kinetics, if we understand the electrode designing, so we can of course predict the efficiency of fuel cell or battery, which is our ultimate objective. Now I am coming to the first plot, I think. Now, first condition is that where the overpotential is very low. I am now doing this condition. Now this is our, and of course the general equation of Butler-Volmer equation. This is our general equation. And there are two exponential terms. You see, there are two exponential terms. First is, this part is one exponential for anodic part, and this exponential terms. Now, if the value of overpotential is very less, you see, less than 10 millivolt. So the value of F and N, as you know that F is equal to, generally we write F by RT. You can write like that. And most of the cases I am using the one electron method. So therefore, here generally N, or in some books it is Z, N is equal to 1. So again I just try to understand the things. I am first writing the Butler-Volmer equation, and there are two exponential as I just told you. And suppose this X, in first case, anodic case, X is equal to 1 minus alpha Fn, this part. And second case, X is equal to minus alpha is this part. So what I am getting, in one case I am getting exponential X minus exponential minus X, very simple. And if I expand the exponential, it must be, it should be Ex. And it should be and other factors minus X. And it's like that. So it is simple mathematics. At low potential, if the values of f and n is very less than greater than 1 value. So if I expand the exponential and neglecting the other higher part, so I'll get 1 plus x. Like that, I'm taking only this part. And negative part, but I'm getting 1 minus x. So what I'm getting, Ex is equal to J0 is common. So the value is 1 plus x. This is 1. And the value of x, 1 minus alpha fn. And maybe some other parts. So I have written dot dot dot. Minus e exponential minus x. So that is 1 minus x, 1 minus alpha fn, and then the other parts. Just you solve it. So alpha fn cancel out this alpha fn. So what is remaining? Fn. Isn't it? Fn. So j is equal to j0 fn. So what I am getting, j is equal to j0 f and n. So there is a direct relationship between the direct relation between the current density and over potential. F you can write f by RT also. So again and again I am saying same thing. If the over potential is very low, like less than 10 millivolt, the net current density is J and be directly proportional to the over potential. So you can directly plot a graph between current density and over potential. Sometimes a small question can be asked that prove that at low over potential the interface obeys the Ohm's law. So what is the distinction between the Butler-Volmer reaction and the Ohm's law? I'll just explain, because we will explain. One is the charge transfer resistance. I will explain these things. And then this is the first part at the low over potential, and if the potential is very high, over potential is very high, like 0.12 volt, then of course these two part, this exponential part and this exponential part, this part can be eliminated. So what? J is equal to J0, 1 minus alpha fn. Or you can call that if the over potential is very high, so this part will be vanished. So you will get only J is equal to J0 exchange current density plus 1 minus alpha fn. That can be, if I take the logarithm form also, I can write these things. You all know these things. Now I am coming to the relationship between the Ohm's law and the Butler-Volmer equations. Now you all know that Ohm's law is the relationship between the voltage and the current. Do you know these things? I think everybody is well aware of this Ohm's law. And you know that there is a linear relationship when current increases proportionally with the voltage V. But if I want to use this Ohm's law for any electrochemical reactions, electrode kinetics, then it would be very difficult. It does not account the kinetics of electrochemical reaction occurring in the electrode interface. So we have to relate between that Butler-Volmer equation and the Ohm's law. When the over potential is very low, how do I solve these things? Now we are getting this first point. J is equal to J0 Fn. Suppose in place of F I have written this RT and F. F is equal to suppose RT and F. This part. So, RT upon F. F is equal to, I'm just sorry. So, can I write like this thing that J is equal to J0 over potential RT of F. Now, if I write that J is equal to, you see, eta divided by, I am using in new terms, capital R, subscript C and T. Capital J, small j, eta divided by RCT. Or I can write like that. RCT is equal to N divided by Ji. So this, which looks like the Ohm's law, as I have written there. So J is equal to eta divided by RCT. Of course, it must be R capital. You can write in the small ct, or in some books it is also, you can write like that. So therefore, RCT, that charge transfer resistance, is equal to FRT J0. This is actually. So what is, how do you calculate the charge transfer resistance? F divided by RT, because it is 1 by RCT. So RCT is equal to F, RT and J0. So RCT or charge transfer resistance is not a fixed resistance, but it is a dynamic quantity. And of course it is influenced by the kinetics of the redox reactions. So it is this, if we calculate the charge transfer resistance, and because this charge transfer resistance is based on the kinetics of the redox reaction and of course that exchange current density, Ohm's law plays a role, and that will be useful for the resistive element. So it is a one small part, you can call it a distinction between the Ohm's law and the, if you don't understand, so you can directly write only one line that at lower potential in Butler-Volmer equation, that part is, or that equation obeys the Ohm's law. But why it obeys the Ohm's law, I am just giving the explanation for that. Now the first part is over, when the over potential is low. Now I am coming when the over potential is high. Now again I am writing the same thing, same equation, but when over potential is small and positive, the current is anodic, and if it is negative, the current is cathodic, and is the normal. You can write F or RTF, so there is no problem. So what I am getting, you have seen that I am getting J, very simple equation, J0 and F and okay, in some books it is, the current density can be denoted as the I, small I, I0. And as I told you that F can be, small f can be RT by F. RT by F, I am just RT by F. So simple thing, what I can write like that? I can write like that J0 is equal to F or in place of RT by F. So there are two processes. The direct, I can plot a graph in y-axis. I can take J J0, and in some books it is also Fn and volt, and current is ampere, like that. So, or simply you can plot a between the current density and eta. So there is no problem for that. You can, with the help of this plot, you can also calculate this J0. Now, if the over potential is very large and positive, in that time, in low potential, I am just talking about the 10 millivolt, you see, very low. And here it is 0.12 millivolt. So there are two conditions also there. That means the values are very large. That can be positive also. Values are very large, but that can be negative also. So just this part is negligible. That means anodic current process is dominant. You follow my point? If the over potential is very high, this part is neglected, so I am having only this part, Ex, and X log of whatever it is, we can write like that. If I take the log and other things, J0 and so here I am getting only J is equal to J0 exponential E minus Ks. So if I take the logarithm of this form, so natural log of Ji is equal to natural log of J0 plus E minus alpha Fn. So now you can understand the sometimes in examination question that derive the Butler-Volmer equation, and what is Tafel equation, or sometimes it is called the Tafel plot. Tafel plot. Tafel plot. That means we plot a graph between log of current density and over potential, whatever, on the basis of that plot. So today I am not discussing the Tafel equation. There is a separate lecture. Those who want to learn about the Tafel equation, they follow my fourth lecture of this electrochemical series, that is the Tafel equation. There is a complete 1 hour lecture of the Tafel plot. Now just the last part, now I am showing some of the graphs. Now I think you can understand there are two parts, low over potential and the high over potential. Now I am showing some of the curves, or sometimes it's called the polarization curve. That is the last part of my lecture. I must confess that there are many books available, like Bockris and Reddy and Physical Chemistry by Atkins. I am using this equation from the books of Physical Chemistry by the Atkins. So you can check it from your book, whatever the different types of plots. And in addition to that, there are a large number of research papers, study materials are available in the literature regarding the discussion on this Butler-Volmer plots. So in my case, I am using only symbolic plot. I am not giving any specific system. There are many systems, hydrogen system, copper system, K3 FeCN6 to K4 FeCN6 system. ferric to ferrous system. There are so many systems. But deliberately, just in order to understand the student, I am using a symbolic Butler-Volmer plot, or sometimes it is called the polarization plot. One thing is very clear, that in this right hand side is the values are positive. It may be 1, 2, 3 volt or like that. And this side may be minus 0.1 like that. It is a minus value, negative value. Similarly, here is also the current density ampere per centimeter square, maybe positive values, maybe value negative. That is my objective. And this particular point you can show, this particular. So this type of, sometimes it is called the hyperbolic signage function, nonlinear type of thing. But what is important here, that if you just understand, if you just see it very carefully, that here the value of overpotential is greater than 0, this is a high value you can call it. So if I just compare this part, you see, naturally the exchange current density or current density is also very high. If I just take this part of this thing. So that means this anodic current is predominating. So it is definitely, this part is called this anodic polarization oxidation part. Whereas in contrary, you see here very less value of potential, less value, and the value of current density is also very less. So that is, I am just giving only one example. So that part is the cathodic polarization. And this is a general temperature, maybe 298 K, and alpha maybe 0.5 like that. It's a general plot. Similarly, if you want to learn much more about this thing, so you can see some typical plot. It is a symbolic part, not specified any reactions like that. Second, another part here, there are two systems. One system is A, another system is B. A system is denoted as, you see, this blue color. This is A system. It's a very symmetric type of A system. And another system is B, you see, this type of color. Both the color is blue, no problem. What does it indicate? That this case, A, this side is positive, this side is negative, same thing. This side is positive value, this side is negative value. And the plot between, again, current density and what does it indicate? That this A shows the high exchange current density. You see, whereas this B is low exchange current density. You are also seeing two dotted, both are red color. That shows the individual electrode reaction of that high current density, this part. I am not showing the electrode process of the B system. I am using only one. Now what is the conclusion? And as usual, if I see this in the previous plot, you have seen that this part is anodic part, this part is cathodic part. So again, I am showing here this same thing, the anodic region, and that is the cathodic region. But what is important is that in order to flow the current, if the low exchange current density, that case, so we have to increase the values of overpotential. N is required to flow. High values of N is required to flow that current. So on the basis of this Butler-Volmer plot or polarization curves, one can predict that whether your reaction is occurring or not, current is flowing or not. So that is the one example. Again, I am not giving any sort of example, but if you want to see, you can refer the books of Atkins and others, books like Bockless and Reddy. They have given large number of examples. Now the third, last point. Now you cannot think that, and of course this part is exchange current density of this part, this part. Now you can think that suppose it is also maybe 298 K, alpha is 0.5 like that, n is 1, n means n number of electron changes, n or z is 1. Suppose you want to know what would be the effect of if the alpha values is different, 0.5, 0.25, 0.1, 0.75 or 1 like that maximum. Or this J0 is also different, ampere. What you will do? First condition, dependence of the anodic and cathodic current density on the over potential or transfer coefficient. So what we will see, that what would be the effect of if the value of alpha is very low, what happened? Less than 0.5, and if the value of alpha is higher than 0.5, what happened? Number one condition. Number two condition, that what would be the effect of current densities? Dependence of the current density on the over potential for different values of transfer coefficient. Let me see these two graphs. First is that effect of exchange current density at constant values of alpha. Temperature is 298 K. Again, it is a symbolic, as I told you. I am not giving any values here. Maybe this side is positive, maybe 1, 2, 3, 4, 5, like that. And you see that A ampere per second square. And here is also negative. Now, there are three colors. One is J, red color is the medium values of, and this color is low exchange current density, and blue color is high current density. So I am getting three types of results. So in first case, you see the value of J, exchange current density, is very high. So at very low over potential, but the current density is very high. That means if J is very high, a large value of eta is required to produce a small current. If this indicates that very fast electrode kinetics, because if you see here, this value is very low, even 0. If the value of J is very low, you see very high value is required. That is slow. Actually, it should be not like that. It should be up to that actually. ये नहीं होगा, इतना दूर नहीं आएंगे, like that. So slight. So this is the condition. That means it is directly related to the exchange current density. If it is fast, high value, then of course there is a fast kinetics. If it is low, very well, it is sluggish. It's not like up to this actually. This may be up to this, maybe up to this, like that. And now this is the effect of alpha. Again, temperature is 298 K. So we are using different types of alpha values, maybe. And of course, we plot a graph between same thing. This side is positive, this side is negative values of overpotential plus exchange current density, there is negative current exchange density. So it is a cathodic direction. Naturally, this side is green side and this is the red side. What? And you know that ampere you can count ampere per centimeter square. So first is that what is the effect of transfer coefficient, or sometimes it is called the symmetry factors. Now again the same thing, that if the transfer coefficient value is very low, you see, that part is not visible here. That means the anodic direction is easier. And you have already seen that at lower over potential, anodic current is predominating. And in higher values, of course, not 0.8 like that. So the cathodic direction is easier. And in this intermediate is like that. It is a standard symmetrical curve. 0.5 is the standard value. So if it is lower, so anodic direction is easier, and if it is higher, cathodic direction is easier. So the charge transfer coefficient is often referred as the symmetry factor. So therefore I have written symmetry factor, because it determines the dependence of the current density on the overpotential. Otherwise you would have a similar type of plot. So there are three types of plots: higher, lower, and the normal cases. So that means it determines the dependence of the current density on the overpotential. Now I am giving some of the results obtained by that different types of plot, and I am taking these values from the books of the Atkins, I think 2018 edition. You can get these values at page number 801, and some of literature. So I am using the first reaction, hydrogen evaluation reactions, the very common reactions, and everywhere you see the value of exchange current density. Now temperature is 298, alpha values is also almost 0.5, 0.5 standard value. So it is hydrogen evaluation reactions. It is a reduction process. It's very important. So I am getting, you see, 7.9 into 10 to the power minus 4. If I change the electrode, then it is nickel. So this is 6.3 into 10 to the power minus 6. If it is lead, you see, value is very low, 5 point into 10 to the power 3. So as I told you in my introduction part, there is a limited experimental data. Data are not very limited. Now I am giving definitely two different types. You see, electron is here also there. K3 efficiency. What is your observation, student? If I compare these two systems, number one is only one electron transfer, two electron, one electron transfer. Second, there is no bond breaking system here, or the bonds are very weak. The values of exchange current density is high as compared to those values. The high values. So it is a one simple observation that if there is a one electron transfer system and there is no, in redox system involves no bond breaking. So J0 values are high if I compare with this system. Okay. So let me conclude. Today I have discussed the third part of my presentation, because it is a long series of lectures. Butler-Volmer equation 1, the fundamental Butler-Volmer equation. Part 2 is the derivation of the Butler-Volmer equation. Deliberately, I have divided into 3 parts because it's very lengthy, otherwise it would be a very lengthy lectures. And third is the application part. And just to make clear to the student that what is the difference between the, I am not saying is a difference, I should say it is a most simplified forms of Butler-Volmer equation, the Tafel plots and the Tafel equation, which is applicable for the high over potential and is a log form. You know, if I generally write this normal form of the Butler-Volmer equation and plot a graph between, simply we plot a graph between the current density and eta, or in some places you will see that I upon I0, J upon J0, eta and F also, that is possible. But if I take the Butler-Volmer equation, so it is a logarithm form. But validity is all over potential, the Butler-Volmer plots are applicable. But there is a limitation is that, as we have said, the 0.12 volt for high potential only. And in Butler-Volmer, it is a non-linear type of plot. And in Tafel, it is a log plot. Use modeling simulation. Experimental data are limited, but in experimental analysis are available, and both the equations are, both the plots are useful to determine some of the parameters. That means on the basis of Tafel plot or Butler-Volmer, you can determine the value of alpha, you can determine the exchange current density also. So thank you very much. Next time, if time permits, I will discuss some of the numerical problems of Butler-Volmer equation as well as the Tafel plot. Thank you very much.